Alright, hello everybody and welcome to a new problem that is going to show us how powerful the two pointers technique is. This problem is called the longest subarray with at most k distinct integers. So let's read the statement together. We are given an array of integers and we should find the longest subarray that contains at most k distinct integers and return its length. If we take a look at the first example, we are given an array consisting of 5 integers and our k equals 2. And the output is 4. So this means that we have a subarray of length 4 which has at most 2 distinct integers. And indeed we do. This is the subarray. 1, 2, 1, 2. The only distinct integers are 1 and 2. There are 2 of them, so obviously this subarray is a valid one, right? If we try to find a longer valid subarray, it's not going to happen, right? Let's say we try the one of length 5, which is indeed the whole array. As you can see, there are 3 distinct integers here, 1, 2, and 3. So the answer is 4. Now, for the second example, again, an array of 5 integers, but k equals 3. And the answer is 4. Yeah, because we have this subarray of length 4, which contains 3 distinct integers, 1, 2, and 3. The other subarray of length 4 is this one, but it's not a valid one because it has 4 distinct integers. And if we try to find a longer subarray, you're not gonna, because this one of length 5, which is the whole array, has of course 4 distinct integers. So the statement is pretty simple. I hope you understood the problem. And yeah, let's jump into the solution. First of all, we have encountered a lot of problems of this type. It is that type of problem that asks for the longest subarray which has some property. So coming up with a brute force approach is indeed straightforward. We know how to do that. In order to find the longest subarray with some property, we will have to try out each and every one of them, take into account only the ones that are valid. So for each subarray, check if it is valid, and if so, and also its length is greater than what is our current answer, update the answer with that length and continue. So let's break the brute force approach into the stages. The first stage is, of course, trying out each and every subarray. What is a subarray defined by? Its starting position and its ending position. So we have to basically try out each and every pair of indices I and j. Now, for each pair of indices I and j, stage number 2 is to check if the subarray nums of I and j is a valid one. So we need a way to count how many distinct integers are there. So how many distinct integers in the subarray I and j are there. And once we have computed this number, check if it is indeed less than or equal to k. And if so, update the answer, right? Cool. Awesome. Now, the first stage, we know how to do this. It involves 2 nested for loops, one for setting the value of I and the other one for setting the value of j. Now that we have the subarray I and j, we need to count how many distinct integers are in that subarray. Is there a problem that we have already solved that actually asked for this? And yes, it is. That problem is number of distinct values. So please, if you don't remember how to solve that problem, go and watch that lesson again because we are going to use that principle. Let's take a quick look at how the code for this brute force approach looks like. As you can see, I have used the variable answer, initialized it with 0 to store my answer, so I'm going to return it in the end. And what I'm going to do is have those 2 nested for loops to try out each and every subarray, I and j, and then I'm going to call the function how many distinct of nums of I and j. This function is going to compute for me how many distinct integers are in the subarray nums of I and j, and if that number is indeed less than or equal to k, I'm going to update the answer with the maximum between what is its current value, so the current solution that I found, and the length of this subarray, which is j minus I plus 1. I'm not going to write the code for the how many distinct function because you can find that solution and the code in the number of distinct values lesson. But again, make sure you understand that lesson, you know how to solve that problem, and the only thing that you need to do is count for only the subarray that starts at position I and ends at position j, and not for the whole array. And this is it. Now, let's analyze the time complexity of this brute force approach. What are my atomic operations here? The return, which is constant, the initialization, which is constant, they both happen only one time, and then I'm going to have this assignment and computing the maximum, also constants. And here I'm going to have an if statement, which calls the function how many distinct and then compares the result with k. So the comparison is obviously constant time, but the tricky part here is that we need to know what is the time complexity of the how many distinct function. And if you remember from the lesson number of distinct values, we have come up with an optimal solution of big O of n. So the number of iterations was equal to the length of the array. Now here, the number of iterations is going to be equal to the length of the subarray because we only solved the problem for the subarray, right? So this is going to be j minus I plus 1 iterations. Cool. And we are doing this for each and every pair I and j that we are trying out inside these two nested for loops. And as you can see, computing the time complexity here is a little bit trickier because the number of iterations that this piece of code does is actually dependent on the value of I and j. So it is dependent on this for loop, which is also dependent on this for loop, right? So one way of doing this is actually writing on paper for each value of I and j, what is going to be this number and add all of them together. So I'm just going to do that, right? First value of I is 0. So I equals 0. Let's see what happens. When I equals 0, the first value of j is 0. So I'm going to have j equals 0. For j equals 0, what's going to happen? I'm going to make 0 minus 0 plus 1 iterations, so 1 iteration. Then, after that, j will become 1. So I'm going to make 1 minus 0 plus 1, 2 iterations. Then j becomes 2, I'm going to make 3 iterations, and so on and so forth until j becomes equal to n minus 1. So I'm going to make n minus 1 minus 0 plus 1 n iterations. So only when I equals 0, I'm making a total of the Gauss sum, which is n crossed n plus 1 divided by 2 iterations. Cool. Now, guess what? I'm going to jump to I equals 1. When I equals 1, again, I'm going to take each and every value of j. J starts with 1. So first of all, j equals 1. What happens here? How many iterations? 1 minus 1 plus 1 is 1 iteration. J equals 2. 2 minus 1 plus 1, 2 iterations, and so on and so forth until j hits the value n minus 1. And I'm going to have n minus 1 minus 1, so n minus 2 plus 1 iterations. So when j is n minus 1, I'm going to have n minus 1 iterations. Again, this is a Gauss sum, and it's going to be equal to n minus 1 crossed n divided by 2 iterations. So as you can see, these two numbers are very similar. The only difference here is that each number in this product is going to be decreased by 1, right? So n became n minus 1, n plus 1 became n. It's pretty simple. You can even take the I equals 2, I equals 3 scenarios, but it's pretty simple to notice that the sum is going to be equal to something like this. Let me erase all of this. N crossed n plus 1 divided by 2 plus n minus 1 crossed n divided by 2 plus n minus 2 crossed n minus 1 divided by 2, right? And so on and so forth until on the last value of I, which is n minus 1, I'm going to have j also n minus 1, and I just have 1 iteration. So it's going to be something like 2 crossed 1 divided by 2. So as you can see, it is the type of algorithm where computing the exact number of iterations is super tricky. Even I don't know how to mathematically solve this, and I don't even care about it because my intuition says that the number is going to be pretty huge. As you can see, this number is obviously less than or equal to n squared. This number is also less than or equal to n squared. This one too, and so on and so forth. And yeah, even this one, if it is pretty small, it is still less than or equal to n squared. So it is the type of time complexity where I won't complicate myself trying to compute this sum. It is definitely useless. I am going to take an upper bound, which is n squared. And because I have n numbers here, all of them less than or equal to n squared, I can conclude that this sum is less than or equal to n cubed. And I'm going to say that the time complexity of this algorithm is indeed big O of n cubed. Of course, I could have also come to this conclusion by just taking the upper bound for each of these lines of code. So j minus I plus 1, of course, is always less than or equal to n. The number of iterations here, no matter the value of I, is less than or equal to n, and the number of iterations here is less than or equal to n, right? And I could have multiplied n by n by n, and I get this big O of n cubed. But because these three lines of code are dependent on each other, I'm not gonna hurry and say it is big O of n cubed. There are a lot of problems in which amortized analysis comes into play, and you will see that this will be actually big O of n squared, or something way smaller than big O of n cubed. So what you should do is always follow the structure, always start with the piece of code on the bottom, compute the exact number of iterations. You see that it depends on the next one. So you try out each and every value of this one, which also depends on this one. So you'll end up doing what I did. And if actually you can't compute this sum, but it's pretty obvious that it's going to be big anyways, and it's not going to get reduced or stuff like that, you can conclude that, all right, let's say it's big O of n cubed. This is very important, okay? So we have come up with a brute force approach of big O of n cubed. I'm going to keep this in a separate lessons because I think it is pretty interesting, and I think it is a very good exercise for you to remember how to solve that problem and to write this algorithm. But what we are going to do in the next video is actually reduce this from big O of n cubed to big O of n squared. Awesome. See you there, guys.